thing. Now you may have, how many of you have heard this saying that 80% of, 20% of the modules cause 80% of the failures. This is the so-called Pareto principle. And the idea is that there is a shortcut that you can take. And this says that there is actually no shortcut. So the people have published some data, and people have tried to find shortcuts which module to choose. And it turns out that the modules which is likely to have more defects are the modules which are bigger. This is of course what you would expect if they have about the same defect density. So this suggests that there is really no shortcut. You test a module, testing time for a module should be approximately proportional to its size, unless they have different defect densities. So if you start with a project, if you have a project where you inherited some modules, which are presumably more reliable, because they have already undergone some testing, then you basically need to focus on the modules with higher defect density, so that eventually at the end, all the modules have the same defect density and hence the same failure rate. And there's a numerical example which you might as well take a look at this numerical example. Let's look at this. Any questions or comments so far? So this, so basically our finding, they're sort of intuitive to me, but they're sort of contrary to popular wisdom. So popular wisdom says that there are shortcuts, and there's this Pareto principle. But what I find is that there are really no genuine shortcuts. In fact, I have been thinking of writing a paper on it, but I'm afraid that people will be offended by it, because people believe in shortcuts. So everyone wants to believe that there is a shortcut. And if you tell people that no, there's no shortcut, you just have to test them approximately proportional to their size, unless they have different defect densities. Okay, so let's take a look at a numerical example. So basically I constructed this example. So I constructed this example based on my understanding of the connection between the model parameters and the software sizes. So let us say we have these blocks, and let me call these blocks B1 to B5. So we have these 5 blocks, and the sizes are 1, 2, 3, 10, and 20,000 lines of code. So the last B4 and B5 are much bigger blocks of software. And let's assume defect densities are, so initial defect densities let us assume R 20, 20, 20, 25, and 30 defects initial defect density per 1,000 lines of code. And we want to come up with an optimal testing strategy. So these are the values I assumed for constructing the example. And now here I will say, I will pretend that these things are given, and actually I calculated them based on these here. So let me give you the values of beta 1 I. So let us assume that beta 1 I is given to be 7 multiplied by 10 raised to minus 3, 3.5 multiplied by 10 raised to minus 3, and this is 2.3 multiplied by 10 raised to minus 3. Sorry about that, I guess I had to make that a little small. And then for B4, it is 7 multiplied by 10 raised to minus 4. And for B5, it is 3.5 multiplied by 10 raised to minus 4. So this is B1I values, which actually are based on these. And let's assume that failure intensity values at time 0 are given by this. Notice that they have the same defect density, and hence they have the same failure intensity. So the failure intensity is directly proportional to defect density. More defects you have, higher would be your the rate at which you would encounter defects. And let's assume f sub I. Now let me assume here that f sub I is proportional to the module size, and if I assume that I get let's say 5. Next I have, sorry for writing so small. Now, since this module, these two modules are much bigger. Most of the time, these two are executing. So this is executing about 50%, 55% of the time. This is under execution about 30% of the time, and these are under execution much smaller fractions of the time. So, okay. So these are the given values for the example. These are the given values, and you have to apply the optimization problem and find out the optimal testing time and the resulting failure intensity that you would achieve at the end of the testing time. So here are the optimal values. Optimal testing time and optimal failure intensity after you are done with testing, and it turns out to be, let me round the numbers, So notice that you spend a lot more testing time here for two reasons. These two modules are bigger, and also they have higher defect density, right? And what would be the final optimal failure intensity? That's the optimal failure intensity after you are done with testing. So notice, at the end, everything is equal. Any questions or comments? Okay, let me come back to one of the questions you had in that feedback module. You have you have a CD system, and let's say I forget which one was supposed to be more reliable. Oh, I think I have that here. Let's see, where is that? So this is I guess it's alpha and beta, and I had mentioned that our alpha is less than our beta. And so you have the question, you can put another one like this and make it more reliable, or you can have another one of type beta and make it more reliable. And it is given that the reliability of this is less. So you have to find out which one will give you more reliability. And the answer, as you will remember, I guess you all did it correctly. Incidentally, I have posted a copy of the solutions. And actually in one of the questions I had a little error which I have corrected. So if you go there, you will find the corrected version. Go to MCT. So all of you say that you will duplicate this one and not this one, right? And you of course have the mathematical argument there, or actually some of you have used the numerical values. So it is generally better to work on, if the cost is the same, it is generally better to make the less reliable components more reliable. So basically find out your weakness, where the system is weak, and make it stronger there. Now there is another reason that was not there in that I did not consider the cost function. And it turns out that cost function usually is like this. Let me see. Cost function as a function of reliability. Here's the reliability. And of course, the maximum reliability is 1, and lowest reliability is 0. And the cost function would usually go, and here's the cost. So let us say